All right, so let's talk about block matrices here. Just a few minutes. So this sometimes gets left out of the discussion for undergraduate linear, which is unfortunate because it's actually kind of an important topic for applications, if nothing else. So here I introduced some kind of sneaky physics notation, which is called the Einstein notation. So Einstein, one of his, so I think it's a bit of a joke, but one of his great contributions was to remove sums in physics. So if an index is repeated in physics, that means it's summed over, and the kind of index it is will indicate the kind of sum. So like mu mu would be a space-time sum, so it ranges from 0 to 3, 1 time 3 space, you know. In contrast, if you have like a j, well, that would be a spatial index, and so like if a j was repeated, it would be a sum from 1 to 3. So I don't know, physicists have a lot of trouble writing summation, I guess. I'm just joking. It is actually a very, very efficient and important notation if you're doing hundreds of pages of calculation, trust me. But anyway, so instead of writing that, we write that. Instead of writing this, they would write that. Okay? But there's more. The kind of letter you use indicates the kind of sum. So like, we could split m and n to indices into like m and mu and n and nu. So, you know, m ranges over m plus, like the full range of m plus mu and n plus nu for n. And then if you were to use this kind of interesting, weird notation, then the matrix AMN would have 4 different kinds of blocks. It would have like the MN block, it would have the mu nu block, and then it would have these mixed ones like m nu or mu nu, mu n rather, and likewise for B. And so if you looked at the multiplication of two matrices, which would look like this, right? This would be, just to give you, this would be AB, ABMJ, right? And here there's a sum over n, which is implicit, right? Big N. Well, then that breaks into the sum over the little n and the sum over the little nu. But then m and j have different cases, all right? By the way, if you don't, this is not something I would test on because this is really, again, this is physics notation. I'm just spending a minute to tell you about this wild other world of notation. The result I'll get to in about 2 minutes is important though, okay? So if you want to skip ahead, feel free. Anyway, so mj, little m, little j, or it could be little m, and then the nu case, or it could be the mu and the little j, or the mu and the gamma, finally, right, m gamma rather. And in each case, it's coming from, you know, a particular sum of particular kinds of pieces of the matrix A and B, blocks, if you will. And so you can summarize these 4 different things by looking at multiplying the A matrix and the B matrix in terms of multiplying these submatrices. Right, there's these 4 different submatrices, these so-called blocks to the matrix A or the blocks to the matrix B. All right, and so anyway, getting to the point, if we have a partition of the matrix A into these submatrices, these blocks, A11, A12, A21, A22, and likewise for B, and if the blocks are set up so that the following down here makes sense, then when you multiply these matrices, this matrix of matrices out, then this is the block multiplication rule, which in a nutshell says that you can multiply 2 block matrices as if the blocks were numbers, provided you don't, you got to be careful not to commute, right? So like A11, B11, plus A12, B12, and then A21, B11, A22, B22, B21. It's important that I put the A's first and the B's second because, again, they don't commute. But that's the rule for block multiplication. All right. And you can extend it for more blocks, just the same. So an example that is kind of near and dear to my heart is these 4x4 matrices, which I'm forming from 2x2 blocks. So this actually, Cosh and Cinch and Cosh, this corresponds to a space-time a velocity transformation, a so-called boost in special relativity. This, as I've mentioned before, is a rotation in the plane, or some plane in this context. And so if I look at lambda being a boost in the rotation, and this is a different boost in a different rotation, these are examples of what are called Lorentz transformations on four-dimensional space-time. But I've written them in terms of blocks where the blocks are either zero or a boost or a rotation. And well, you can multiply two such Lorentz transformations by multiplying the blocks. So I just use the block multiplication to multiply. And oh, fun fact, if you multiply two of these, then the hyperbolic angles just add. If you multiply two rotation matrices, then the rotation angles just add. That comes from the adding angles formula for sine and cosine and cosh and sinh respectively. There's a bunch of details to actually see that this claim is true, but you know, there's a kind of a neat example of block multiplication. This next page is a little bit more kind of, you know, plain vanilla linear algebra kind of calculation. You know, I've got a matrix with blocks A, B, C, and the question is, if I've got this block decomposition of M, what does it take for M to be invertible? And so what I do is I look for a inverse, which also has a corresponding block decomposition, and I'm assuming all the blocks are square to keep things, you know, relatively benign. And if I do that, and I block multiply M and its alleged inverse, M inverse, I'm looking for D, E, F, and G. I don't know what they are at the outset. Then the block multiplication says I have to get this, and this equal to the identity. But the 4x4 identity, by the way, can be looked at as two by two identities blocked with two by two zeros. So this notation is, oh, excuse me, who says it's 2 by 2, right? I never said how big M is. This could be a n by n. This could be a k by k for all we know, right? Although I think I said that they were square, didn't I? So I guess that forces, it may force the size of these to be the same. If I said, did I say B was square? I think we're forced to have these blocks be the same size then. Anyway, for these two things to be equal, we have these separate equations, one for each block, and I work through here to how to solve it, and eventually I come to this, this formula for the block inverse, which is this. And, you know, kind of funny, if you look at the case that the blocks are numbers, it reduces to that 2 by 2 inverse formula I showed you earlier. Anyway, I think I'm way over time at this point. Just a word or two to tell you. The reason people like blocks is because, you know, when we put these things on a computer, and for big matrices, if you can find a block of zeros, it like simplifies the calculation vastly. So parsing the problem into blocks is, I thought, very, very useful for numerical methods. The other reason blocks are interesting is because of quantum mechanics, and also, in some sense, a lot of what's called representation theory in mathematics, in some sense or another, could be seen as an attempt to find blocks. A block representation of a transformation would be often a more simple version of the transformation. We'll actually talk about that a little bit later for linear transformations, and here the so-called Jordan form is an example of something that's what's called block diagonal. Block diagonal is it's almost a diagonal matrix, but it's at least just got blocks of matrices down the diagonal which are non-zero. Let me not be vague and show you. So if this is a matrix like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And if it's got zeros everywhere else, this would be an example of what's called a block diagonal matrix. All right, well, that's it. So come tomorrow, also known as Monday, we will pick up with systems of equations. So thanks, guys. Bye.